Hello class, today we're going to go over 11.5 alternating series. And an alternating series is a series whose terms are alternating from positive to negative. So let me just show you a quick example. 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus, and that going so on and so on. That we could rewrite like this, of 1 over n. That's the Riemann sum for the series to be written out. But that's all the alternating series is. We're going to alternate from positive to negative and negative to positive, depending on how you're going to start. And what's cool with this is we can determine if these series are going to converge or diverge. And so we have an alternating series test. And what the series test tells us, if we have a function, if we have a series that's alternating, we can do two things to it. We can compare the next term to the previous, and if the next term is smaller than the previous term for all of the terms, that's the first condition, as long as that's satisfied. And then if we take the limit of the term as it goes to infinity, the series as it goes to infinity, if it goes to 0, then we know that this series is going to converge. So let me show you an example of this so you guys can see what the alternating series does. So in this example, the first condition, right, was to show that the previous term is bigger than the next coming term. So we can look at this and we say, okay, so b of n plus 1 has to be smaller than b sub n. So if we take our nth term, we end up getting, I'll show this to you, it's going to be 1 over n plus 1. And then the one before it is going to be 1 over n, right? Because we can see that the term is smaller than the next. And the reason we can see that is what's happening as n gets bigger. All that's happening is the n was 1, so it was 1. The n was 1, and then here it was 2, 3, 4, and you can see when we get to n, you're going to get 1 over n, and then the next one's going to be 1 over n plus 1. And so you can see that the denominator is getting bigger and bigger and bigger, and so that means that the overall number is getting smaller. So that's satisfied, so we're good there. For the second condition, we're going to take the limit as n goes to infinity of that bn term, right, which is 1 over n. And as n goes to infinity, we see that this is going to go to 0. That satisfies the second condition, and it says if it satisfies the first and second conditions, then we know that this series, the series is convergent. And convergent just means, again, that it's going to one specific value. But that's the series test. You go to the next term, see if it's bigger. If it's bigger, then you go on to take the limit of the b to the nth term and see if that's going to be equal to 0. If b is equal to 0, then we know it's convergent. So let's do another example. So in this example here, it's not really easy to show the first condition. So what I want to do is demonstrate the limit piece first. So this would be the second condition. And let's see if the second condition can give us something. So remember, it's the limit as n goes to infinity of b of n. And so that would be the limit as n goes to infinity of 3 to the n over 4n minus 1. Well, that's equal to the limit of 3 over 4 minus 1 over n as n goes to infinity. That's going to give me 3 over 4. That's not equal to 0. So if we go back to the condition, it only tells us that it's convergent if it satisfies these two conditions. We don't have enough information to tell if it's divergent. So in order to see if it's divergent, we're going to have to do something. And so if we went back to 11.2, there was the test for divergence. And the test for divergence told us that if we take the limit as n goes to infinity of our a to the n term, we should be able to, if it doesn't exist or if it doesn't equal to 0, then our series was divergent. So that's what we're going to look and see if we can do here. So as n goes to infinity of negative 1 to the n over 3n over 4n minus 1, we can see that this does not exist because it's going to always oscillate. Basically, it's going to be, you can think of it as 3 to the 4th, but with the negative 1 there, it's going to go back and forth, oscillating. So it's not going to equal some number. And so since this is do not exist, by the test of the divergence, this series, therefore this series diverges. And again, that was from 11.2, and it's by the test of divergence. So there's going to be some things that you're going to have to write down, jot down, so that you know all of these tests. And this was in 11.2 again, just so you can see the test for divergence. But I tried to use the alternating series test to see if I could see that this thing was converging. Since it was inconclusive that it was converging, then I needed to show that it was diverging, and I was able to do that with the test for divergence. Okay, let's look at another problem. So in this problem here, we're trying to decide if this is going to be convergent or divergent. And so what I want to do is I'm going to look again at the b sub n, and my b sub n is going to be n squared over n cubed plus 1. And we can see that the denominator is bigger than the numerator. And so as n gets bigger and bigger, we can see that this thing is going to be decreasing, right? But we don't know if that's going to make it, converge. So we need to look at some things. So what we're going to do is we're going to look at this in terms of a related function. And so let's look at it as a function of x squared over x cubed plus 1. And then let's take the derivative of that to see what happens. And so we should get x over 2 minus x cubed over x cubed plus 1 squared. Write that down. X cubed plus 1, that quantity squared, and that's by the quotient rule, right? And so what we're going to do here too is, because our series goes from 0 to infinity, we're only going to be looking at positive x's, okay? So that's important for us to look at. So we want to see, all right, so f prime has to be less than 0. When does that happen? And the reason I'm looking at this is because remember that the derivative gives a slope. So if the slope is positive, it's increasing in value. If the slope is negative, then it's decreasing in value. So we want it to be decreasing so that we can see that, determine if we're getting something that's going to eventually converge. And so we see that this thing is going to be less than 0 if 2 minus x cubed is less than 0. Well, that implies that x is going to be greater than the cube root of 2. And we can see that anything bigger than the cube root of 2 is going to give us a decreasing value. So we know then, by looking at the derivative, that f of x is decreasing from the cube root of 2 to infinity. Okay, so now to be able to do the alternating series test 1, we're going to go, all right, f of n plus 1, that is greater or less than f of n. that's our implication for the b of n plus 1 being less than b of n, right? That first condition for the alternating series test. And this happens when n is greater than or equal to 2. And you could see that by just plotting in the n plus 1 and the n plus 2. And you could see that that would happen, that this is occurring. And then, so we have that happening. And then in part 2, we need to show that the limit as n goes to infinity of b of n. And so the limit as n goes to infinity of b of n would be the n squared over n cubed plus 1. And we see that that would be the limit as n goes to infinity of 1 over n, 1 plus 1 over n cubed. And that would give us 0, right? And so the alternating series test told us that if b of n plus 1 was smaller than b of n, that checks. And if the limit of the b of n was equal to 0, then we'd know that we had a convergent series. And so what this implies is that the series is convergent, right, by the alternating series test. And so this really is important that we know these two conditions very well, right? We need to know these two conditions very well to be able to do these problems. And there I showed it right here and here. And so this will obviously take some practice, but it's something that I believe you all should be able to do and manage fairly well. All right, let's see if we can find. Let's talk about the alternating series estimation theorem. And so what the estimation theorem is telling us here is if we have this function that alternates, right, and we can show that it satisfies the alternating series theorem, and that the next term is bigger than or equal to 0 but smaller than the previous term. So it satisfies the two conditions, but it satisfies the two conditions, and then what ends up happening is that we have some remainder, and that remainder has to be smaller than our b to the nth plus 1 term. So I'll explain this to you guys so you can understand this. So let's look at this example that we have, and then I'll use this theorem to clarify it. So the first thing that we need to do by the alternating series theorem test is to show that this thing is in fact going to hold true. And so when I do the n plus 1, I'm going to go 1 over n plus 1 factorial. But that I can break it up to be n factorial, n plus 1 factorial, which will be less than 1 over n factorial. And all I really did there was use factorials as a term, right? So we know that n plus 1 factorial is equal to n plus 1 times n, times n minus 1 times n minus 2, all the way till we get to multiplied by 1, right? So what I'm doing is showing that the n plus 1 factorial is going to have, not only is it going to have, I don't need that factorial there, sorry. It's just n. Yes, I do. I did it by composition. Now from here, what's going to happen is we see that that's the same as this, and then there's a divisor here. And so this divisor that's happening here clearly makes this denominator bigger than this one. So this whole term is bigger than this whole term. So that satisfies condition number 1. Condition number 2, then we need to show that we are between, there's n factorial, and 1 over n, and we see that that's going to go to 0. So 1 over n factorial is going to go to 0, right? Just because as n gets bigger and bigger and bigger, our denominator is going to make our whole term smaller and smaller and smaller. So we can see that this goes to 0, and so that's awesome. That satisfies the second condition to the alternating series test. And so now we're going to play and see what we can get as a sum. So I want to be able to show that to you. So then S is equal to 1 over 0 factorial minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial minus 1 over 5 factorial plus 1 over 6 factorial plus, oops, this would be minus 1 over 7 factorial plus dot dot dot, right? And so what we end up seeing is this is going to be 1 minus 1 plus 1 half minus 1 sixth plus 2, 4 times 3 times that, 1 over 24 minus 1 over 720 plus, oops, let's see, did I get that? Let me see if I'm right. 24 is, what's 5 factorial? Let me get that real quick, sorry. 5 times 4 times 3 times 2 is 120, oops. Plus 1 over 720 minus 1 over 5,040 plus dot dot dot, right? And now, one of the things we can see here is we want 3 decimal correct here, and so in this problem, since we want to be correct at 3 decimals, we need the term that we're adding to have an addition or subtraction that's going to be 0.000 and then a number. So we need to make sure that we're at a big enough number that we're adding zeros to it. So in this example here, our 7th term, right, because we're at 1, 2, 3, 4, 5, 6, 7. It ends up being the 8th term, but we call it b to the 7. Because b to the 7th is going to be what's correct. And then the 8th term is where our error is going to occur. So we see that b to the 7th is equal to 1 over 5040. Well, that's smaller than 1 over 5,000, which would have been 0.0002. And we see that S sub 6 is 1 minus 1 plus 1 half minus 1 sixth plus 1 over 24 minus 1 over 20 minus 1 over 120 plus 1 over 720, and that approximates to be 0.368056. And our error, right, the remainder error, is going to be S minus S sub 6, which has to be less than that b to the 7th term, and that's going to be 0.0002. And so we know that while we're approximating, we know that we have exact correct values for 368. We may be off on the next digit 0, but we're correct at 3 digits here. So this is correct to 3 digits. In linear algebra, you'll be doing some of this error analysis and adding decimals, and you end up doing it by paper and pencil and calculating with a basic calculator. It's a pain, but you end up being able to see that you don't really need calculators to find complete accuracy to significant digits. But we're not doing that here yet. So this is the alternating series. Notice that in all of these alternating series, the positive and negative in terms of comparing the series wasn't an issue. It wasn't until we were trying to find the sum that we cared about if it was positive or negative, or what was going on with the negative 1 to the n or n plus 1 powers. All right, I'll leave that to you there. The homework should be up for you tonight, so you guys can work on that. And I wish you all the best. Take care.